Now we'll come to comparison tests of the second type. So we're going to write comparison tests of the second type. Now in this, suppose we have two series, summation un and summation vn, such that this summation vn, it is convergent. Then if there exists a natural number m such that un plus 1 upon un is less than equal to vn plus 1 upon vn for all n greater than or equal to m, then we'll say this series summation un will also be a convergent series. Now again here we won't use it in this form. We'll use practical comparison test of the second type. And here we have a very important test which is called as D'Alembert's ratio test. So it will be this D'Alembert's ratio test. So in this test, what we'll do is, if we have this series of positive terms, summation un, then we'll work out this limit n tends to infinite un plus 1 upon un, and suppose this limit is L. Now if L is less than 1, then this series it converges. If L is greater than 1, then this series it diverges, and if L is equal to 1, then the test is inconclusive. This series, in case of L equals 1, it can be either convergent or divergent. Now another equivalent form for this D'Alembert's ratio test is this limit n tends to infinite un upon un plus 1, and it is equal to L. So basically it's the same, it's just that we have taken the reciprocal of limit. Now in this case, if L is less than 1, then the series diverges. If L is greater than 1, then it converges. And again, if L is equal to 1, test is inconclusive. Now let us take an example. Say for example, we have to find convergence of the series factorial n plus 1 upon 3 to the power n. Now in this case, un is factorial n plus 1 upon 3 to the power n, and un plus 1, it is factorial n plus 2 upon 3 to the power of n plus 1. Now we'll find this limit n tends to infinite un upon un plus 1. So it will be this limit n tends to infinite. Now this is factorial n plus 1 upon 3 to the power n divided by un plus 1. So it will be 3 to the power of n plus 1 upon factorial n plus 2. Now this 3 to the power n will cancel, and this factorial n plus 1 will cancel. So we'll get this as this limit n tends to infinite 3 upon n plus 2, and value of this limit is 0, which is basically less than 1. And if it is less than 1, then in that case this series it diverges. So this series, it is a divergent series. Now another example is, suppose you have to check convergence of the series factorial n upon n to the power n. Now in this case, un is factorial n upon n to the power n, and un plus 1 is factorial n plus 1 upon n plus 1 to the power n plus 1. Now we'll find this limit n tends to infinite un upon un plus 1. So it will be this limit n tends to infinite factorial n upon n to the power n divided by, now here it will be n plus 1 to the power n plus 1 upon n plus 1 factorial. Now this factorial n and factorial n plus 1 will cancel. So we'll have this n plus 1 and this n plus 1 will also cancel. So we can write this as this limit n tends to infinite, and this is 1 plus 1 by n to the power n, which is 1 to the power infinite form, and it is this standard limit, which is e. And since e is 2.7 something, it is greater than 1, which means this series, it is a convergent series. Now let us take another example. Suppose we have to test the convergence of this series 1 plus x square upon 2 plus x to the power 4 upon 4 plus x to the power 6 upon 6 up to infinite. Now in this case, un is x to the power 2n upon 2n if we omit this first term. Now this un plus 1 will be x to the power 2n plus 2 upon 2n plus 2. Now we find this limit n tends to infinite un upon un plus 1 will be this limit n tends to infinite. Now this is x to the power 2n upon 2n into 2n plus 2 and x to the power 2n plus 2. Now this x to the power 2n will cancel. Now here coefficient of n is 2 and 2, so it will be this one. So answer to this limit will be 1 upon x square. Now if x square is greater than 1, then 1 upon x square will be less than 1. In that case, this series, it diverges. So this is the case for divergence. And if x square is less than 1, then 1 upon x square will be greater than 1. In that case, this series, it converges. And if x equal to 1, test fails. Now when x is equal to 1, we'll have this series, which is 1 plus 1 by 2 plus 1 by 4 plus 1 by 6. So in this case, un will be 1 upon 2n. And if we take another series, which is harmonic series, summation 1 by n, then this limit n tends to infinite un upon bn will be 1 by 2, which is unequal to 0 and finite. That means behavior of both the series will be same. Now we know that this harmonic series, it diverges. So at x equal to 1, this series, it is a divergent series. So this series, it diverges if x square is greater than or equal to 1, and it converges if x square is less than 1. Now for testing convergence, we can use another test which goes by the name Cauchy's nth root test. Cauchy's nth root test. Now in this case, suppose we have this series summation un, which is a series of positive terms. Then we'll find this limit n tends to infinite un to the power 1 by n, and suppose this limit is L. Now if L is less than 1, then this series, it converges, and if L is greater than 1, then this series, it diverges. And if L is equal to 1, then in that case, this test is inconclusive. Now generally we use this nth root test if power to this entire expression is some function of n. Say for example, we have to test for the convergence of this series. N varies from 1 to infinite, 1 plus 1 upon under root n to the power minus n to the power 3 by 2. Now clearly it's an infinite series with positive terms, and in this case un is 1 plus 1 upon under root n to the power minus n to the power 3 by 2. Now here we use Cauchy's nth root test. So we're going to find this limit n tends to infinite un to the power 1 by n, which is this limit n tends to infinite 1 plus 1 upon under root n minus n to the power 3 by 2 to the power 1 by n. So it will be this limit n tends to infinite 1 plus 1 upon under root n to the power minus n to the power 1 by 2. Now this is standard limit and its value is e to the power minus 1, which is 1 upon e, and 1 upon e is less than 1. And since value of this limit is less than 1, it means this series, it is a convergent series. Another example is, we have to test for the convergence of this series 2 square upon 1 square minus 2 upon 1 to the power minus 1 plus 3 cube upon 2 cube minus 3 by 2 to the power minus 2 plus 4 to the power 4 upon 3 to the power 4 minus 4 by 3 to the power minus 3 up to infinite. Now in this case, this un will be given by this n plus 1 to the power n plus 1 upon n to the power n plus 1. So it will be this n plus 1 upon n whole to the power n plus 1 minus n plus 1 to the power n whole to the power minus n. Now in this case, this power is minus n. So for this also, we'll use Cauchy's nth root test. So we'll write this limit n tends to infinite un to the power 1 by n, and it will be this limit n tends to infinite. Now we take this power 1 by n, so this n and n will cancel, so we'll get this as n plus 1 upon n to the power n plus 1 minus n plus 1 upon n whole to the power minus 1. Now we can write this as this limit n tends to infinite, and this is 1 plus 1 by n to the power n plus 1 and minus 1 plus 1 by n to the power minus 1. Now this is standard limit, which is e, so it will be this e and then minus 1 to the power minus 1. So value of this limit is 1 upon e minus 1, and 1 upon e minus 1 is less than 1. That means this series is a convergent series. So now we have discussed two tests, ratio test and Cauchy's nth root test. Now basically ratios test is a corollary of nth root test, and therefore Cauchy's nth root test is superior than D'Alembert's ratio test. Now there will be cases where D'Alembert's ratio test will be inconclusive. Then in that case, we can use Raabe's test. Now in this test, what we do is, for this positive series un, we'll find out this limit n tends to infinite n into un upon un plus 1 minus 1, and suppose value of this limit is L. Now if L is greater than 1, then this series, it converges. If L is less than 1, it diverges. And if L is equal to 1, then this test is inconclusive. Say for example, we have this series which is 1, 3, 5 up to 2n minus 1 upon 2, 4, 6 up to 2n, and it is x to the power 2n upon 2n. Now in this case, un is 1, 3, 5 2n minus 1 upon 2, 4, 6 2n x to the power 2n upon 2n, and un plus 1 will be this 1, 3, 5 up to 2n plus 1 upon 2, 4, 6 up to 2n plus 2 x to the power 2n plus 2 upon 2n plus 2. Now first we'll use ratio test, and for this we'll find this limit n tends to infinite un upon un plus 1. So it will be this limit n tends to infinite. Now un is this 1, 3 up to 2n minus 1, and this is 2, 4 up to 2n x to the power 2n upon 2n, and here it will be this 2, 4, 6 2n plus 2 2n plus 2, and this is 1, 3, 5 2n plus 1 x to the power 2n plus 2. Now we can write this as this limit n tends to infinite. Now this 1, 3 up to 2n minus 1 will cancel, and here this 2, 4 up to 2n will cancel. So we'll get this as 2n plus 2 whole square upon, and the denominator will have 2n plus 1 into 1 upon x square. Now it is an infinite limit in n. Coefficient of n square is 4 in the numerator and denominator. So if we take this limit, it will be this 1 by x square. Now if x square is greater than 1, then 1 upon x square is less than 1. In that case, this series it diverges. And if x square is less than 1, then 1 upon x square is greater than 1. In that case, this series it converges. From the ratio test, we can work out the convergence if x square is either greater than 1 or less than 1. But if we take x as 1, in that case, value of this limit will be 1, and then this ratio test will be inconclusive. So this ratio test, it is inconclusive when the value of x is 1. So what we'll do is, for x equal to 1, we are to use Raabe's test. So now we are going to find this limit n tends to infinite n, and this un upon un plus 1 minus 1. Now will be this limit n tends to infinite n. Now this un upon un plus 1, it was this 2n plus 2 whole square upon 2n plus 1 into 1 upon x square, and since we are taking x as 1, it will be 1 minus 1. Now we can write this as this limit n tends to infinite n, and here it will be this 4n square plus 4 plus 8n minus 4n square minus 2n upon 2n and 2n plus 1. Now this 4n square will cancel. We can write this as this limit n tends to infinite 6n square plus 4n upon 4n square plus 2n. Now it is an infinite limit. Highest power is n square. So value of this limit is simply 3 by 2, and 3 by 2 is greater than 1, which means this series it converges. So this series it converges if the value of x is 1. So for x equal to 1, ratio test failed, but we got the result using Raabe's test. Now an alternative to Raabe's test is logarithmic test. So rather than using Raabe's test, we'll use this test for this positive series un, and we'll find this limit n tends to infinite n log un upon un plus 1, and suppose this limit is L. Now if L is greater than 1, then this series it converges. If L is less than 1, then this series it diverges, and if L is equal to 1, then the test is inconclusive. So what we'll do is we'll perform ratio test, and if it fails, then rather than taking Raabe's test, we can use logarithmic test. Say for example, we have test for the convergence of this series 1 plus x upon factorial 1 plus 2 square x square upon factorial 2 plus 3 cube x cube upon factorial 3 up to infinite for x greater than 0. Now if we omit this first term, we can write un for the series as n to the power n into x to the power n upon factorial n. And un plus 1 will be n plus 1 to the power n plus 1 x to the power n plus 1 upon factorial n plus 1. Now first we'll use D'Alembert's ratio test. So we'll find this limit n tends to infinite un upon un plus 1. So it will be this limit n tends to infinite. Now this is n to the power n x to the power n factorial n, and here will be this n plus 1 factorial upon n plus 1 to the power n plus 1 and x to the power n plus 1. Now here this factorial n will cancel, so this is n plus 1. N plus 1 will also cancel, so we can write this as this limit n tends to infinite. Now this is 1 upon here x to the power n will also cancel, so it will be this 1 plus 1 by n to the power n into x. Now this is standard limit, which is e, so it will be equal to 1 upon ex. So from ratio test, we got this limit as 1 upon ex. Now this is your L. So if 1 upon ex, it is greater than 1, then the series converges. So for x less than 1 upon e, this series it converges. And when x is greater than 1 upon e, this series it diverges. Now when x equals 1 upon e, value of L is 1. In that case, this test it fails or it is inconclusive. So now what we'll do is, at x equals 1 by e, we'll determine its convergence using logarithmic test. So we can write this as this limit n tends to infinite n log un upon un plus 1. So it will be this limit n tends to infinite n log, now un upon un plus 1, it is this value. Now we have taken x as 1 upon e, so we are going to write this as e upon 1 plus 1 by n to the power n. So this is when the value of x is 1 by e. Now we can write this limit as this limit n tends to infinite. Now here we have this n. Now log e is 1 and minus, we'll take this power out, n log 1 plus 1 by n. Now this is limit n tends to infinite n, and this is 1 minus n. Now we can use series expansion for log 1 plus x. So it will be this x minus x square upon 2 plus x cube upon 3. It will continue up to infinite. Now we can write this as this limit n tends to infinite. Now this 1 and 1 will cancel, so it will be this n and plus 1 upon 2n minus 1 upon 3n square. We multiply this n, and if we take this limit n tends to infinite, we'll have this limit as 1 by 2, which is less than 1. That means in this case, this summation un it diverges. So this logarithmic test, it is an alternative to Raabe's test. To summarize so far, first we have to use D'Alembert's ratio test. If ratio test fails, we have to go to either Raabe's test or logarithmic test. And if Raabe's test also fails, then we can use De Morgan's and Bertrand's test. So next we have De Morgan's and Bertrand's test. So for this infinite series un of positive terms, we'll find this limit n tends to infinite n into un upon un plus 1 minus 1, which is basically Raab's test, and then minus 1 into log n. And suppose this is equal to L. Now if L is greater than 1, then it is convergent. If L is less than 1, then it is divergent. And if L is equal to 1, then the result is inconclusive. So if Raab's test is inconclusive, we'll use De Morgan's and Bertrand's test. Say for example, we have to test for the convergence of this series. 1 square, 3 square, 5 square up to 2n minus 1 whole square upon 2 square, 4 square up to 2n square. Now in this case, un is 1 square, 3 square, 5 square up to 2n minus 1 whole square upon 2 square, 4 square up to 2n square, and un plus 1 will be 1 square, 3 square, 5 square up to 2n plus 1 whole square upon 2 square, 4 square up to 2n plus 2 whole square. Now we'll find this limit. N tends to infinite, un upon un plus 1. So it will be this limit. N tends to infinite. Now we can adjust this 1 square, 3 square, 2n minus 1 square upon 2 square, 4 square up to 2n square into, now this is 2 square, 4 square up to 2n plus 2 square upon 1 square, 3 square up to 2n plus 1 whole square. Now we are going to cancel a lot of terms. So here 2n minus 1 whole square will cancel. So in the denominator we'll have 2n plus 1 whole square and the numerator will be 2n plus 2 square. So it will be this 2n plus 2 square, which is limit n tends to infinite 4n square plus 8n plus 4 upon 4n square plus 4n plus 1. Now here highest power is 2. So this value is 1. That means this ratio test, it fails. Now once ratio test fails, we have to use Raab's test. And for Raab's test, we find this limit n tends to infinite n and then un plus 1 minus 1. So it will be this limit n tends to infinite. Now this is n. Now un upon un plus 1, this is 4n square plus 8n plus 4 upon 4n square plus 4n plus 1 minus 1. That will be this limit n tends to infinite. This is n. That will be this 4n square plus 8n plus 4 minus 4n square minus 4n minus 1 upon 4n square plus 4n plus 1. Now here 4n square will cancel. We'll get this as this limit n tends to infinite. That will be this 4n square plus 3n upon 4n square plus 4n plus 1. Now here degree in the numerator is 2 and in the denominator is also 2. So value of this limit is 4 by 4, which is 1. That means this Raab test, it also fails. So now we have to use De Morgan's and Bertrand's test. Now here we will find this limit n tends to infinite n un upon un plus 1 minus 1 into log n. Now this entire expression is from Raab's test. So this is 4n square plus 3n upon 4n square plus 4n plus 1. So we can write this as this limit n tends to infinite will be 4n square plus 3n upon 4n square plus 4n plus 1 minus 1 log n. Now this is this limit n tends to infinite. Now this 4n square will cancel. So here we'll have minus n plus 1 upon 4n square plus 4n plus 1 into log n. Now what we'll also do is we'll multiply and divide everything with n. Now for this first limit, highest power is 2. So value of this limit is minus 1 by 4. And then we have this limit n tends to infinite log n by n, which is infinity upon infinity form. Now we use L'Hopital's rule. It will be this minus 1 by 4 and then this limit n tends to infinite 1 by n, which is 0, and 0 is less than 1. That means this series summation un, it diverges. So if ratio test fails, we are going to go to Raabe's test, and if Raabe's test fails, we are going to go to De Morgan's and Bertrand's test. Now an alternative to Raabe's test is logarithmic test. Now if logarithmic test fails, then we can go to something called as second logarithmic test. So now we'll discuss second logarithmic ratio test. So if we have this series summation un, then we'll find this limit n tends to infinite n log un upon un plus 1, which basically is logarithmic test, minus 1 into log n, and suppose this is equal to L. Now if L is greater than 1, then this series, it converges. If L is less than 1, then it diverges, and if L is equal to 1, then the result is inconclusive or test fails. Say for example, we have to test for the convergence of series 1 to the power p plus 1 upon 2 to the power p plus 1 into 3 upon 2 into 4 to the power p, and will continue up to infinite. If we ignore this first term, then we can write this un as 1 into 3 up to 2n minus 1 upon 2, 4 up to 2n whole to the power p, and we can write un plus 1 as 1, 3 up to 2n plus 1 upon 2, 4 up to 2n plus 2 whole to the power p. Now first we'll use ratio test, and for this we'll write un upon un plus 1, and we divide everything. This 2n minus 1 will cancel and this 2n will also cancel, so we'll get this as 2n plus 2 upon 2n plus 1 whole to the power p. Now first we'll use D'Alembert's ratio test. So it will be this limit n tends to infinite un upon un plus 1. So it will be this limit n tends to infinite 2n plus 2 upon 2n plus 1 to the power p. Now coefficient of n in the numerator and denominator is both 2. So 2 upon 2 is 1. So this is 1. That means this ratio test, it fails. So D'Alembert's ratio test, it fails. Then we'll go to logarithmic test. And in logarithmic test, we'll find this limit n tends to infinite n log un upon un plus 1. So it will be this limit n tends to infinite and then n log, and this is 2n plus 2 upon 2n plus 1 whole to the power p. Now we can write this as this limit n tends to infinite n into p, and here will be this log and we can write this as 1 plus 1 by n upon 1 plus 1 by 2n. We can also write this as this limit n tends to infinite np, and this is log 1 plus 1 by n minus log 1 plus 1 by 2n. Now we'll use series expansion. We can write this as this limit n tends to infinite n into p. Now this is 1 by n minus 1 by 2n square plus 1 by 3n cube, and here it will be 1 by 2n minus 1 by 8n square, and so on. So it will be this limit n tends to infinite np. Now this is 1 by 2n, and here it is minus 3 by 8n square. When we multiply this n, we'll get this limit as p by 2. Now if p is greater than 2, then this summation un, it converges, and if p is less than 2, then summation un, it diverges. Now for p equals to 2, this logarithmic test, it fails. So for p equals to this n log un upon un plus 1, it is 1 minus 3 by 4n, so on and so forth. Now we use second logarithmic ratio test, and for this we'll find this limit n tends to infinite n log un upon un plus 1 minus 1 into log n. So it will be this limit n tends to infinite. Now this n log un plus 1 is this value, and then minus 1. So it will be this minus 3 by 4n plus higher powers of 1 by n into log n. Now what we'll do is we'll multiply and divide everything with n. Now we multiply n here, we'll get this as minus 3 by 4, and then we'll have this limit n tends to infinite log n upon n, and we know that log n upon n is 0, which is less than 1. That means this series summation un, it diverges when the value of p is 2. So this is how we use these tests. To test convergence of an infinite positive series, we can also use something called as Cauchy's integral test. Now this Cauchy's integral test, it says if we have a function ux which is non-negative decreasing integrable function, so we have this non-negative decreasing integrable function which is associated with the sequence un, which we can write as un for all positive integral values of n, then we say this series summation un, where n varies from 1 to infinite, it converges if and only if this integral from 1 to infinite ux dx is convergent. So if we have a non-negative decreasing integrable function ux which corresponds to this sequence un and this infinite series, it will converge if this integral is convergent. Now say for example, we have to discuss the convergence of the series summation n varies from 1 to infinite 1 upon n square plus 1. We have already discussed this convergence using comparison test, and we know that this series, it converges. Now here we'll consider this function ux, which is 1 upon x square plus 1, and if we find u dash x, will be minus 1 upon x square plus 1 whole square into 2x, and will be less than 0 when x is greater than or equal to 1. It is non-negative, decreasing, and integrable function. So what we'll do is we'll find this integral from 1 to infinite ux dx, and the way to write it is this limit t tends to infinite, this integral from 1 to t, and ux is 1 upon x square plus 1 into dx. That is this limit t tends to infinite, and we know that this is tan inverse x from 1 to t, so we'll have this as this limit t tends to infinite tan inverse t minus tan inverse 1, and tan inverse 1 is pi by 4. Now if you put t as infinite, tan inverse infinite is pi by 2, so it will be this pi by 2 minus pi by 4, which is simply pi by 4, which is a finite value. That means this integral, it is convergent. So this corresponding will also converge. We can use this Cauchy's integral test to decide the convergence of generalized harmonic series, which was this summation n varies from 1 to infinite 1 upon n to the power lambda, and we know that if lambda is greater than 1, then this series it converges, and if lambda is less than or equal to 1, then this series it diverges. Now we'll prove this using Cauchy's integral test. Now we take this first case. When lambda is 1, then we have the series as this summation n varies from 1 to infinite 1 by n. So we'll take this corresponding function 1 by x. Now this 1 by x, it is integrable and continuous and decreasing. Now this integral from 1 to infinite ux dx, it will be this integral from 1 to infinite 1 by x dx, which is log x from 1 to infinite. Now it will be this log infinite minus log 1, which is 0, and log infinite is infinite. That means this integral, it diverges. So this summation 1 by n will also diverge. Now if we take the second case, when lambda is greater than 1, then we can write this as this summation n varies from 1 to infinite 1 by n. Now here ux will be 1 upon x to the power lambda. Now u dash x will be minus lambda x to the power minus lambda minus 1. It is less than 0. That means this function, it is non-negative, decreasing, and integrable. So we'll find this integral from 1 to infinite ux dx, which we want to write as this limit t tends to infinite, this integral from 1 to t, and this is x to the power minus lambda dx. Now will be this limit t tends to infinite. Now this is x to the power minus lambda plus 1 upon minus lambda plus 1 from 1 to t. So it will be this limit t tends to infinite, and here will be 1 upon 1 minus lambda 1 upon t to the power lambda minus 1, and then minus 1 upon 1 minus lambda. Now since lambda is greater than 1, this power is positive, so it will be this 0 minus 1 upon 1 minus lambda, which is finite. That means this integral, it converges. So this series 1 upon n to the power lambda, it converges when lambda is greater than 1. And if lambda is less than 1, then here this power will be negative. In that case, this integral, it won't converge. So I'll leave the solution to this third case to you. Now let us take another example. We have to test for the convergence of the series summation 1 upon n log n whole square, where n varies from 2 to infinite. Now corresponding function is ux, so it will be this 1 by x log x whole square. Now we find u dash x will be minus 1 upon x square log x to the power 4 into, now this is log x square plus 2 log x. Now since x is greater than or equal to 2, this log is positive, these even parts they will be positive, and we have this negative sign, so that means u dash x is less than 0. So this function is non-negative decreasing function and integrable. So to test for the convergence of this series, we'll use this integral, this limit t tends to infinite 2 to t ux dx, which is this limit t tends to infinite from 2 to t. Now ux is 1 upon x log x whole square into dx. Now we can write this as this limit t tends to infinite from 2 to t, and this is d log x upon log x square, which is this limit t tends to infinite minus 1 upon log x from 2 to t. So it will be this limit t tends to infinite will be 1 upon log 2 minus 1 upon log t. Now when t tends to infinite, log t tends to infinite, and 1 upon infinite is 0, so it will be equal to 1 by log 2, which is finite. That means this integral, it converges, and if this integral converges, then this series n varies from 2 to infinite 1 upon n log x square will also converge. So this is how we test convergence of infinite series with positive terms.